Welcome to this introduction to IPv6, transition to IPv6 for service providers. So actually this is a little bit about my experience. I have been IPv6 for about 15 years and in about 20 years in Cisco and TCP/IP. You can find me on the internet and I will be very happy to answer to your questions if you need anything about routing and switching or IPv6 in general. So I would like to first introduce the generations of tools that we have seen for transitioning to IPv6. So the first generation was when IPv6 was introduced in '96. So the dual stack and the static tunnels were the first tools which were introduced to permit an experimental backbone, the 6-bone, to be created. And at the same time, NAT and private addresses permitted to extend the life of IPv4 for 20 more years. But it also broke a few things about the internet, like the peer-to-peer model, which was broken by NAT. So IPv6, one of the goals of IPv6 is to get rid of NAT, and which is a good thing. The second generations of tools were the first tools which permitted for service providers to deploy IPv6 services. So the first tools were for MPLS backbone service providers. So basically at the end of the 90s, most service providers were deploying MPLS backbone, and it was quite difficult to tell them that actually they would need to start an IPv6 backbone instead. So Cisco started to develop 6PE to permit an immediate deployment of IPv6 over MPLS IPv4 backbone. Later came 6RD, which permitted to develop an IPv6 service over IPv4 backbone, and at the same time we have seen idea to use the IPv4 address, public addresses, with more efficiency, and the idea was to use one more time NAT and another level, another stage of NAT to share IPv4 addresses among customers. And also at the same time we have seen protocols to translate between IPv4 and IPv6 with the first tool which was NAT-PT, which is now deprecated because it was doing too much things, as we are going to see later. The third generation actually was started at the same time than the second generation, but actually the goal is to get rid of carrier grade NATs, because service providers don't like much the idea of running NAT in the backbone, stateful NAT. Stateful protocols in a backbone are never very something the service provider wants to see, because you must do a very careful capacity planning to make sure you will plan enough resource to manage the translation. If you don't, you will have problems. So stateless architectures are being studied, like A+P architecture, which is providing the same benefits than carrier grade NAT, but without having to run stateful NAT in the backbone. And this is something which is currently being studied and very interesting for the service providers. So if we look at the transition deployment for service providers, so the 6-bone was not really for service providers, it was a test bed for testing IPv6. It was actually built up with static tunnels over IPv4 backbone, and it was not really scalable for service providers. So service providers started to develop IPv6 services with 6PE and 6VPE over MPLS backbones, and then later French service providers invented 6RD, which also permitted to deploy IPv6 service over an IPv4 backbone without MPLS. And once a service provider has finished this transition and is running a native IPv6 backbone, he may still need to support IPv4 customers. So solutions for that is to run DS-Lite. With DS-Lite, we will see that we can support IPv4 customer, and we support these customers as a service providers running an IPv6 backbone. And also a solution which is needed for the customers who have migrated to IPv6 completely and still needs to access IPv4 content. Then NAT 6.4 is going to translate IPv6 to IPv4 and will permit the customers to access some IPv4 content from an IPv6 only network. There are some other tested protocols, as I have already explained, like the third generations protocols, but these are for the moment mostly tested. So the first tools which were used for helping the transition was network address translation protocols, and NAT 4.4 and IPv4 private addresses in the 90s was the very first example. Some people think that NAT is an IP feature which was there since day one for IPv4, but actually NAT was only a workaround to deal with address depletion, but NAT 4.4 extended the life of IPv4 for 20 more years, but it also have broken many features of the Internet. And IPv6, one of the goals of IPv6 is to get rid of NAT to get these features back. IPv6 to IPv4 translation were also proposed still since 2000 with a protocol called NAT-PT, which was doing so much that it was not very scalable. It was doing NAT 6.4, NAT 4.6, address application layer gateway for DNS, FTP, and everything. So it was really, the performance were ugly, and it is now deprecated and replaced by something which is doing less, which is NAT 6.4 and DNS 6.4, and which only permits for IPv6 only customers to access IPv4 content. We also see service providers doing a lot of tests, and in some cases implemented carrier grade NAT solutions, which actually is the principle is to run NAT in the service provider backbone, so we can share a public IPv4 address among multiple customers and save addresses. So again, the first tool which was provided were dual stack and static tunneling in '96. It has permitted the 6-bone to be built, and it was a test bed to test many applications, many protocols, but it was not something for service providers to provide a service for customers. First attempts to run something more scalable were automatic tunnels with 624. So 624 solves provides two solutions. One solution provided by 624 is to automatically provide you with an IPv6 prefix, because there is a reserved block, which is a block starting from 2002, which is a block reserved for 624 addresses. And then the 32 bits which are following are it is actually the 32 bits of your IPv4 public address on the Internet. So this is a unique address, and this way your IPv6 /48 prefix is also unique, and it can be subnetted. You have 16-bit for subnetting, and so two problems solved. One problem is that you don't need to configure the destination IPv4 address of the tunnel, because the destination IPv4 address is derived from the IPv6 address, and also you don't need to request an address, because an IPv6 address is automatically provided from this block reserved. So if you see here the example, 2002 is 2002, C0 is 192, 46 is 70, and 1 is 1. So this is a /48 prefix, which is used for the site on the right-hand side. And same principle for the left-hand side, with 192 C0, 44 is 68, and 1 is 1. And so again, this /48 prefix can be subnetted in many prefixes, in many subnets. And last thing about 624 is that to access the IPv6 Internet, public 624 relay are provided to access the IPv6 Internet. But as this is a fixed prefix 2002, the public relay are not controlled by the customer, and it cannot be used again by a service provider. So a service provider came up with the idea to customize this prefix to make it possible to deploy a service, because it was no longer a 2002 prefix, but a prefix that can be customized for each service provider. So you still need a 6RD CPE, and you need a 6RD BR border relay, which is going to be your gateway to the IPv6 Internet. So basically, the 6RD CPE is configured with the address of the border relay, and when it detects that the destination is not local, it forwards the packet to the border relay for the border relay to switch the traffic out to the IPv6 Internet. So again, same principle than 624. Difference is the prefix, no longer 2002, but a prefix customized for the service provider, and then the IPv4 public address of the customer, which is following, and then the interface ID for each machine inside your network. And this is how your 6RD address is built. Again, it is following exactly the same principle as 624, with the difference that the prefix is no longer 2002 at the beginning, but a prefix which can be customized for each service provider, and so the service provider can control the relay and the return path. So when destination is local, the IPv6 packet is encapsulated in IPv4, and the IPv4 destination address is the local destination address. If the IPv6 destination is not belonging to the same domain, then it must be forwarded by the border relay. So in this case, the residential gateway, the CPE, is configured with the border relay address, and instead of encapsulating the traffic directly to the neighbor, it forwarded to the border relay to get sent to the outside, to the IPv6 Internet. So why this is such interesting solution? The cost, because you need only one tunnel and not a tunnel for each customer. So it is very cost effective, and many service providers are, the latest example I had was Yahoo, who chose 6RD to provide a service using an IPv4 backbone. For the customers, service providers with MPLS, there is no choice. It is 6PE or 6VPE. And again, the beauty is that you do not need to change the backbone. You just need to add the 6PE at the edge, and you will have immediately provided an IPv6 service to your customer. Once the service providers have completed its migration to IPv6, it may still need to support IPv4 customers. So how can we do this? One solution is to use DS-Lite. DS-Lite is a solution where we actually tunnel the traffic from the customer to the service provider. So it is encapsulated within IPv6, and when it arrives at the service provider, it is decapsulated, and the private address is translated to a public address before it is sent to the IPv4 Internet. And again, because NAT is performed by the service provider, the same IPv4 public address can be shared by many customers, so which is a good solution. What to do now for customers who have completely migrated to a full IPv6 solution, and these customers still need to access IPv4 content? So the solution today is NAT 6.4 DNS 6.4. As latest example I have was a mobile phone operator who is providing IPv6 service only, and they plan to use NAT 6.4 because more and more content is now IPv6 reachable. And so they think that there will not need too much translation, and NAT 6.4 will not be so much solicited because most of the traffic will be IPv6 native. So how NAT 6.4 is working, basically, the principle is quite simple. By opposition to NAT-PT from the beginning, the DNS 6.4 and NAT 6.4 are in two separate boxes. So basically an IPv6 only client is requesting an IPv6 address for the name h2example.com. The DNS64 is looking for an IPv6 address, but if it cannot find an IPv6 address, it will get an IPv4, but it will translate to IPv6 using the well-known prefix 64FF9B, and then the IPv4 address coded in in hexadecimal, like C0 for 192, 242, and 0141. Then, once the address is loaded, we can send a TCP SYN to the destination. The packet is routed using normal IPv6 routing to the NAT64 box, which has the prefix 64FF9B. By the way, something about NAT64, DNS64 is that NAT64 comes in two flavors. It can be stateless or stateful. In stateless, it is a one-to-one translation. One IPv4 address for one IPv6 address. With the stateful version, it is possible to save IPv4 address and use the same IPv4 address for many IPv6. Another protocol to save IPv4 address is double NAT, or NAT444. The idea is that the CPE is no longer translating a private address to a public address, but a private to a private, and then it is only at the service provider that the private address is translated to a public address. So doing this, it becomes possible to share a public address among multiple customers, which was not possible before. So this looks nice, but it is not without problems. The first one is a scalability problem, scalability issue. How many translation the LSN should be able to manage? So how can we size the LSN box to make sure it will have enough memory, enough CPU to manage all the translation? Difficult. So we can set a limit, but it means that when the limit is reached, there is no more service, no more access to the Internet. Also, a problem is that it is a single point of failure. So if an LSN box is reloading, it is all the clients, all the customers which are going to reload will need to restart their application to log in again. Another problem is a network design issue. We translate private to private. So what happens if the customer is using the same private address than the address which is used between the service provider and the customer? So we may have a problem. If we have a duplicated address, we know that IPv4 is not working very well. Another possible problem with this is if we have two customers behind the same LSN box. If the two customers are behind the same NAT box, the packet will come back with a source address which is going to be a private address, and we know that the firewall don't like it very much. A firewall which is seeing a packet coming back from the Internet with a private address usually it is filtering this packet out, it is dropping the packets. So which means that we would need to translate all traffic, and including the local traffic, which is which is going to load the LSN box very much. So that's a summary of the problems that we have with double NAT. So scalability and single point of failures, but also network design like overlapping address or source address being a private address, which for a firewall can be a problem. Another solution to support customers is DS-Lite. Again, DS-Lite can be used if the link between the service provider and the customer is running IPv6. So in this case, the CPE at the customer is not running NAT anymore. The traffic is tunneled to the service provider, and it is only at the service provider that the IP packet, the address is translated to a public address. Another solution is 4RD. 4RD is also about encapsulating IPv4 in IPv6, but with 4RD there is no assumption about the NAT running either at the CPE, either in the service provider backbone. So if there is no assumption like this, so if we want, we can still run NAT at the CPE as we were doing, for instance, with other protocols before. The last generation, as I was stating at the beginning, service providers are not very happy running NAT in the backbone because, again, it has scalability issues, it is a single point of failures, it is a lot of problems to manage for service providers, and it is also breaking many things. For instance, you cannot run a server at home anymore. You know, when you are running NAT, for instance, simple NAT, it's possible to configure a static translation on your CPE, and then you can run a server at home. This is something we can do with simple NAT. With double NAT, it's no longer possible. And there are many problems like this. Double NAT is not something without any problems. So it can be a solution in some very well-defined, very well-controlled environments, but it cannot be a solution for everything. So A+P is a nice solution. Actually, A+P provides the same benefits that carrier grade NAT, which means that A+P actually permit to share a public address among multiple customers using the source ports to multiplex the address, which means that each customers will not have the full range of source ports available. Each customer will only have a range of ports which will be for each site. So if the hosts are running A+P, it is no problem. Each host knows that it only has a given range of ports and cannot use all the possible source ports. If the hosts are not updated, It means that we need to have a router at the edge which is going to do some kind of translation to make sure that the packets which are going out of the site are not going to use ports which are not allocated to this site. So this is a translation, but it is not as heavy, as complex as NAT. It is a very simple translation. So this is one function of A plus P. Another function, and this function can be in the first proposal, it is run by dIVI protocol, which is a stateless 464 protocol. dIVI is able to do this, to share a public IPv4 address among multiple sites using a range of ports for each site. The other functionality which is needed by the A plus P border router is to do the encapsulation of IPv4 in IPv6, for instance. And this can be performed by the 4RD protocol, and this is what has been proposed again in the first proposal. The last function is signaling. Signaling is to avoid the manual provisioning of the ports available for each site. So basically, we said that each site has only a range of ports allocated, and this range of ports can be manually provisioned, manually configured, or if we have a signaling protocol, it can be automatic. And if it is automatic, it is as convenient as stateful NATs because it does not require any manual provisioning from anyone. In the first proposal, there is no signaling ready, so the first proposal is only manual static provisioning. So dIVI is the base of the first A plus P implementation. I recommend you take a look at this test, which has been running, and which has permitted to test that dIVI was a good solution for a service provider where multiple sites each site were using a range of ports and not the full range of all ports for all the sites. So that's a very interesting test, and I recommend you take a look at this. You will see that it is really an alternate choice to carrier grade NAT and large scale NAT, which can bring a lot of benefits. I did not have time to explain all the benefits, but there are many benefits running a stateless protocol and A plus P. So thank you very much for attending. If you need more detail, please join me on my blog on fastlaneus.com, and I am giving much more detail about A plus P, about all these transition tools, and I will be very happy to answer your question if you drop me an email. Thank you very much, and bye-bye.